Hey guys, let's get started on our new notes. The stuff is going to be hard. The trees are a different monster in themselves. Just think about a tree forest that is about to attack you. That's what's going to happen on this. Okay, so as you turn to page 12 of your notes, right here at 5.3, you see that you have the conditional probability, and we're talking about independence, and you can see the different additions where it belongs. As we look at this right here, first of all, let's talk about conditional probability. Conditional probability is the probability of one event occurring given another one happened already. Okay, so the bottom line is this: the probability of you going to this college given you got the grade point average. A probability of you going to this college given you got the SAT scores. The probability of you going to prom given you were asked. The probability of you doing well on a test given that you prepared for the test. That all of those were conditional probabilities. And if you heard me, I kept saying the word given. Which takes me to some notations. As I look at this first one, here the probability of A/B, it's not a division sign. This is saying the probability of A given B. So it's saying the probability of A happening given that B already occurred. And as we can see, as we look at the notation, this is the expansion of that is the probability of A and B happening at the same time, given that, or divided by the probability of B. This formula is on the AP test on a sheet that you can use. So when you remember it, or forget it I should say, no worries, because you'll have access to this at all times. Now let's look at its other associated problem. Here, this is the probability of B given A. So this is the probability of B occurring, but A had to occur first. And it's the same ideology like I was saying. The second thing happened with the understanding that the first thing had to happen in the first place. The probability of you driving given that you passed the driver's test. And if you're driving illegally out there, don't want to know about it. Well, actually, I do. Want to know where you are so I can avoid you. Okay? But I want you guys to also see some commonality with these formulas. It was probability of A given B, and that B is in the denominator. Probability of B given A, here the A is in the denominator as it kind of flipped back and forth from math to statistics. The last problem that I want to, formula I want to discuss with you here is the general multiplication rule right here, in which, as we're looking at it, I've got the probability of A and B happening at the same time. But what does that mean? That means here is the probability of A happening. Okay? But when these things are independent, the equation is not just as simple as it was in the past. So the probability of A and B happening is now the probability of A times the probability of B given that A happened in the first place. So we can hear that the idea of the independence. Remember when Jacob got egged? Yeah, Jacob, I'm talking about you. What was the probability? I think he got egged on the fourth one, the 4 out of 12, and then every time another egg was taken away, it was reducing his chance. But we said the bottom line is because, honestly, he should have played the lottery that day. Even though it lowered and lowered, the probability of the first time was 4 out of 7. 4 out of, it was never 4. Let me restate. It was 3 because there was only 3 raw eggs in the first place. So the probability of the raw egg was 3 out of, it was out of 7 at that time. And then after that, by the time it got to him again, there were 2 eggs, and there were 5. So the probability of the first occurrence then times the probability of the second occurrence. So here, as I make a note of this, let's say the probability of the first egg was 3 out of 7. And don't know when it stopped. There were 2 eggs left that were not boiled, but there was a total of 6 eggs. So the probability of this occurrence would have been just multiplying across. But let's keep going with Jacob. Okay, here, by the time it got to him, there were still 2 unboiled eggs, but now there were 5 of them. Now my numbers might be off a little, okay? But the probability of Jacob getting nailed that second time was 12 over 30 times 7, 210. Now you guys could do the math on that. Seriously, homie, you should go play the lottery. Okay? But that's what this is about. Now this is a formula, to be honest, I rarely use. I just do the logic, which is exactly what we did here. And I will be talking about that more tomorrow. But for now, we're going to start to get attacked by the trees. So let's cross out where I see Venn diagram again. And let's just write down tree. And why did I cross out the word diagram? I don't know. Now remember, my pages are always slightly off yours, because when I adjust things, I always mess it up. I want you to take a moment, pause this, write down this tree diagram, and then I will be ready to, then you press again and we'll start talking about it. Welcome back. Okay, now when it comes to these trees, we're talking about 2 events. Either it happened or it didn't happen. So as I look at this right here, a probability of event A happening or event A not happening. So we talked about the car today, the probability of a car or not a car. It either happened or it didn't. Okay, but here's the probability of the second event given the first one occurred. So I can use the idea of a car, the probability of you driving given you had a car. Right here, here's a probability of, remember, these 2 inside branches are complements. So here, as I look at orange, that either it happened or it didn't. Those are complements. Here, these 2 are complements. Remember, complements mean they add up to be 100%. Either they happened or they didn't happen. You can think of it in that way. Okay, here, these 2 are complements as I try to color code. Okay, so here, this branch right here is the probability of B happening, but A occurred in the first place. Its complement is B not happening, but A still occurred. So this is the probability of B not given that A occurred. Right here, as I look at this, here, remember this is the complement. This is it not happening. So this is the probability of B occurring given that A did not happen. Go backwards and look at the branch. Here, and this is the probability of B not happening given that, look at the branch prior to it, that A did not happen. So as I try to find another color, but I really don't want too much, this is the idea. Here's the probability of that given that here it happened here. The probability of this, oh, it happened here, because we're looking at the branches going across. The probability of B, oh, given that A not occurred, and the probability of B not given that A not occurred. I don't know if the arrows help you or hurt you, but after we've talked about all this, we're going to do an example. Now, with all of this, now we do the multiplication. So now let's get into strictly math mode. That times that gives you this. This branch times that branch gives you this. Since I've got some color codes going on here, my orange branch right here times the yellow branch. There's your math. My orange branch right here times my blue branch. And then we go back to that rule that I said to you earlier, I rarely use, and maybe I shouldn't have lied like that. I don't unless I have to use the tree, because I need to realize that once I've done it, that the probability of A times the probability of B, not A, equals to A and B. And I know your thoughts are, well, Miss Yarbrough, don't they just cancel out? And the answer is no, because remember here, as I go back to the egg situation, it was 3 out of 7, and then it was 2 out of 6. And I multiplied, here is event A happening, and here is the second event, as I color code this, just giving this as a basic example. The second event occurring in yellow, given that the orange occurred in the first place. There's no cancellation there. But there would be if these things were independent, but they are dependent upon each other, so therefore it's not. Remember the idea, okay, we just talked about the idea of dependent, so let's talk about dependent a little bit more. Jolly Rancher bags. Always go for the green. I'll buy a bag of them, which I used to always do prior to the health standards California wanted us to watch. And I used to go all through the bags and get the greens because I bought them. I'm going to eat what I want. So every time I took out a green, there was one less green for everybody to choose from, even though all you guys wanted was the blue. It's the same thing. So how did the probability change in that way that I was saying? There's one less green and there's one less piece of candy. So now, in a minute, okay, now I want you to pause again, and as you pause, write down this information and be able to highlight the key, again, information, key pieces of data, and then we'll start back up. So, okay, now, welcome back. Okay, now let's look at this. So Shannon hits her snooze alarm 60% of school days. If she doesn't hit it, she gets to class 90% of the time, makes it to class. Okay, however, when she hits it, she only makes it to class 70% of the time. Okay, on a random day, what is the probability that Shannon is late for school? Now let's write a couple of things down that we just said was applicable. So the probability of hitting the snooze is 60%. The probability of not hitting the snooze is 40%. So here, as I make my tree, this right here is 60, right here is 40, and here is the probability of S for snooze, and the probability for not hitting the snooze. So let's write up here that S equals snooze, hitting snooze button. Now you have a probability right there of 90%. But what happened 90% of the time? If she did not hit the snooze, she made it to class on time. So that means here is the, sorry, there you go. Down there is the branch. Your 90% goes there, but what notation goes there? The probability of on time given that she did not hit the snooze. Now, just like we did before, let's slide up and let's say T equals to school on time. Now, that is your 90%. Now, following the model that I said, remember these inner branches have to add up to be 100%. They're complements. So here, as I turn it, this is the probability of not making it to school on time given that she did not hit the snooze. So if that's 90%, that means that this right here is 10%. So just like that 60 and that 40 gave you a 100, or 0.6 and 0.4 gives you a 1, 0.9 and 0.1 gives you a 1. Now let's see what other percentages I have. Make sure you fill that in. Now right here it says that 70% of the time, okay, if she hits the snooze bar, there is a 70% chance that she makes it to class on time. So right here, remember up here is the making it to class on time. So this is going to be the 70%. This is the probability of she made it on time given that she hit the snooze button. So here, again, because it says right here that if she hits the snooze button, there's only a 70% chance that she makes it to class on time. So here is making it on time, and also the idea that making it on time if she hit the snooze button. Okay, so here, this is utilized right here. Now remember, we can't forget about its complement. So we've got the probability of not getting to school on time given that she hit the snooze button. And we know that's the leftover 30% because that plus that gives you 100. Remember, the inside branches give you a total of 100. Now, let's get into math mode. As we can see, we're just going to be multiplying. 0.6 times 0.7 is 0.42. 0.6 times 0.3 is 0.18. 0.4 times 0.9 is 0.36. 0.4 times 0.1 is 0.04. Please notice that all of these add up to be 100%. Now let's recognize what this all says. Here, this is the probability. We multiplied these two together, so this is the probability of snooze and made it on time. This is the probability of snooze and did not make it on time. This is the probability of did not hit the snooze button and made it on time. This is the probability of here not hitting the snooze and not making it on time. And please remember, this times that gives you that. I'm running out of colors, people. Let's try the purple. And I'm just going to show this times this gives you that. Now, this times this gives you that. And let's try it this way. This times this gives you that. Now, I'm sure you're going to have to do some rewinding on that, or pausing to contemplate what I just said. But now let's answer the question. So the question is, on a random day, what is the probability that she's late? Well, here, remember, T sub C is not on time. So I've got to look everywhere she's not on time. And I'm out of colors, people. But I think I'll just go with the little squiggle. So here, not on time. Here, not on time. Here, not on time. So in other words, this plus this will give me the answer to my question. So the 0.18 plus the 0.04, which is 22%. So the answer to the question is that she is late 22% of the time. Okay, we're done. This is a long one. Sorry, but you can see why. And tomorrow, we're ready to get this party started as we get attacked by the trees. Dun, 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 dun. See you guys tomorrow. Bye-bye.